Hello again. Welcome to lecture 3 of my lectures on power series. Again, this is section 11.8 from Stewart's Calculus, late transcendentals, excuse me. And this is made for my Calculus 2 class. If you have not been sitting in on Calc 2 or have not at one point in your life taken Calc 2, you may not follow this. This isn't meant to just jump in the middle of. Anyway, we have been talking about power series, and we had talked about power series expanded around 0. And let me just remind you of what those look like. Those look like the sum an x to the n, right? Where an's constant and x is the variable. And here I've got something very similar. A power series expanded around a point A here. It's going to be the sum an x minus a to the n. So let me just point out what that looks like. I mean, it's still like a giant polynomial. It's just sometimes it's more convenient to have it around something else. So if I have this one at n equals 0, well, 3 to the 0 is 1, x minus 2 to the 0 is 1, so I get 1 when n equals 0. When n equals 1, I get 3 times x minus 2, so that's plus 3 times x minus 2. When n equals 2, I get, what, 9, right? 9 times x minus 2 squared. And let's go one more out. When n equals 3, 3 cubed is 27 times x minus 2 cubed. And so on down the road. Okay, now, it isn't written in your standard way of writing in increasing values of x. But notice that if I expand all of this, x minus 2 squared, x minus 2 cubed, and combine like terms, it will have a big polynomial again. It's just written in a slightly different way. Okay, and this one again is similar. This is going to be at, oh, guess what? I can't start at n equals 0. Let's start at n equals 1 here. I would give my students extra credit for catching that. Okay, but you can't get extra credit for catching it when I've already caught it. Okay, so we're starting at n equals 1 to infinity. And when n equals 1, I get x plus 4. When n equals 2, I get 1/2 x plus 4 squared. When n equals 3, I get 1/3 x plus 4 cubed, and so on down the road. X plus 4 cubed, not x plus 3. X plus 4 cubed, and so on down the road. And again, if I expand everything in group-like terms, I'll get a big polynomial. This happens to, well, it's got a constant term of 4. It does have a constant term. So what is my a in each of these cases? Well, in this first one, a is equal to 2, right? Because it's x minus a that I'm looking at. In this second case, a is equal to -4. Because it's x minus -4. X plus 4 is x minus -4. So it's x minus a that we're looking at. So these are power series as well as the earlier examples. Notice that in this first one, well, this first one is also a geometric series, right? Let's see if we can find the domain of this first one. And in this first one, we can actually rewrite it. So this is the sum n equals 0 to infinity of 3 times x minus 2 to the n, right? So in this case, r is equal to 3 times x minus 2. And so it is a power series. It's a geometric series, in fact. And as long as that is less than the absolute value of r, so the 3 times x, absolute value x minus 2 is less than 1, as long as that's the case, then this can be written as 1 over 1 minus 3 times x minus 2. Okay, so this is the same as saying absolute x minus 2 is less than 1/3, right? Which is the same as saying -1/3 is less than x minus 2, less than 1/3, which is the same as saying adding 2 to both sides, 2 minus 1/3 less than x, less than 2 plus 1/3. So 2 minus 1/3 So the domain of this is going to be 2 minus 1/3, 6 5/3, right? And 2 plus 1/3, 7/3. Okay, so with the geometric series, it never includes the endpoint, so we don't have to even worry about that. So now let's look at this other thing here. So this is a power series, and we found its domain. The domain of the series is this. You may notice that the domain of this function that I had it equal to, the domain of this thing here is actually, what is that? That's 1 minus 3x plus 6. So that's 7 minus 3x. The domain of this is going to be all x except for 7/3, right? But this equal sign is only holds as long as we're in the domain of the power series. Just a note. Okay, so now let's look here. This one's not a geometric series, but we can still use the same methods we were doing before to find the domain of convergence. And I'm going to use the ratio test on this. Root test isn't that good because of that n in the denominator. It's not raised to the n power. But the ratio test, I'm going to look at the limit as n goes to infinity of the absolute value of the n plus first term, that's x plus 4, to the n plus 1 over n plus 1. So the n plus first term divided by the nth term, x plus 4 to the n over n. And that's going to simplify to limit n goes to infinity, invert and multiply, and of course the only issue that might be positive or negative is x plus 4. Everything else is positive. So I'm going to get n times absolute x plus 4 to the n plus 1 over n plus 1 times absolute value x plus 4 to the n. And of course this simplifies again to limit n goes to infinity of n over n plus 1 times x plus 4, which of course is just x plus 4. That limit's just x plus 4 because n over n plus 1 goes to 1. Okay, so we know it converges absolutely. So it converges absolutely if, where's my pen? Converges absolutely if x plus 4 is less than 1, which is the same as negative 1 is less than x plus 4 less than 1, which is the same as subtracting 4 from both sides, minus 5 is less than x less than minus 3. So it converges absolutely when it's strictly between minus 5 and 3. It diverges if it's on the other side, right? Diverges if absolute value x plus 4 is bigger than 1, which is the same as saying x is less than minus 5 or x is bigger than minus 3. So the only question is what is happening at those two endpoints. If we're finding the full domain of this power series, we need to figure out what is happening at minus 5 and at minus 3. So let me make myself a little bit more room here. Okay, so we're still looking at this particular power series, and we're trying to define its domain of convergence, and we've got it that it converges if x is between negative 5 and negative 3. It diverges if x is less than negative 5 or bigger than negative 3, and we need to figure out what happens at the endpoint. So let's look at x equals negative 5. At x equals negative 5, my series is the sum n equals 1 to infinity of negative 5 plus 4, which is negative 1 to the n over n. And this thing is the alternating harmonic series, so it converges, right? Alternating series test. And at x equals -3, I have the sum n equals 1 to infinity of -3 plus 4 is just 1. So 1 to the n is just 1 over n, and that diverges. Harmonic series. Therefore, the domain on which the domain of the power series is what? Well, it's an interval from -5 to -3. It includes -5, right? It does not include -3. And that's it. Okay, so that's the domain of that function. And next lecture, we're going to talk about the interval of convergence and the radius of convergence for a general power series.